Thanks very much. And thanks very much for giving me the opportunity to give a talk at this conference. Before I start, just want to say I apologize for not being there in person. It's been very enjoyable to join the talks remotely. Unfortunately, we're in the last week of teaching here in Dublin, so I can't fly to Santa Barbara until this weekend. But I will be around for the next 3 weeks if anyone wants to follow up on the discussions from today. So I'm going to talk about an approach to producing waveforms for binary systems, which is a little bit different than maybe we've seen earlier in the week. And that approach is what's called the self-force approach, uses self-force theory. And in particular, I'm going to present some pretty recent results from going to second order in self-force theory. So this is some work that's been ongoing for a number of years. Really, the basis of these waveforms I'm going to show today come from these first 3 papers. The first 2 kind of laid the foundations, and the third one presented the waveforms, and then there's this 4th one which adds on some interesting spin effects into the waveforms. So this is work with a large number of collaborators, including the people down here in the bottom and others who are kind of continuing on from what I'm going to show today. So I guess first up, just for those who are maybe not so familiar with force, I'm going to talk about that, but even before talking about self-force itself, I'm going to give a little bit of motivation for why we might be interested in using this method for producing waveforms. So we've seen quite a bit about LIGO, and there were some mentions also of the LISA mission earlier in the week. And really, for me, the key feature of the LISA mission is represented by this graph of the sensitivity of the detector. So on the x-axis, you have the frequency range, and you notice that it's significantly lower frequency than the LIGO sensitivity is. So LIGO will be over to the right here, kind of around 1 hertz and above. LISA is going to be sensitive to much lower frequency systems. And that's, that opens it up to a whole load of new sources. So there'll be some sources like these streaks, kind of these strong streaks up here, which are very similar in many ways to the sort of binary black hole systems that LIGO is observing every day. They're much bigger black holes, so 10 to the 7, 10 to the 6, 10 to the 5 solar masses, but these signals represent the merger of 2 black holes that are about the same size. And because they're about the same size, many of the existing methods we have for modeling these waveforms for LIGO will carry over, maybe with some extra challenges, but will certainly have a good chance of working for these systems. But if you look at this curve and you look down towards the bottom, there are some other types of signals in here. In particular, there are these kind of dark red streaks, and these represent signals from extreme mass ratio in spirals. And these systems are brand new to LISA. They're not the sort of system we have any hope of ever observing with LIGO because they're just completely outside of the frequency band. And they also bring with them a lot of new challenges in terms of how we produce models for their waveforms. And one of the aims of the LISA mission is to both detect these systems and also estimate their parameters and, as I'll say in a minute, use them as a really strong test of, for example, general relativity. So a little bit more about these extreme mass ratio in spirals. Well, in some sense, they're very similar to the black holes we see in LIGO. They're systems with 2 black holes, but that's about it. That's where it ends in terms of similarity. They're quite different beasts in reality. So the key feature that they have is that they consist of 2 black holes, or maybe a black hole and a neutron star, where the ratio of the masses between them is very, very large. So if you take M1 being the mass of the bigger black hole and M2 the mass of the smaller one, it's not unrealistic to expect the mass ratio in the region of 10 to the 6, whereas LIGO systems are close to 10 to the 0 equal mass, or maybe 10 to 1. And this defining feature of these Emery systems really is a game changer in terms of what their behavior as a system, and also how we're going to model them. So for example, the LISA mission is expected to see over at least 10,000 orbits of one of these systems over its multi-year lifespan. Whereas if we think about LIGO sources, they typically last on the order of a second. So they're much, much longer signals. We're still going to need to be able to produce waveforms that are phase accurate to a very high degree, certainly better than 1 radian. So that's going to be a very big challenge. And as I think Jeffrey mentioned yesterday in his talk, the fact that we have this mass ratio, he was talking about going to beyond 1 to 10 or so being challenging. Here we're talking about 1 to a million or so. That's going to be a huge challenge for existing methods like numerical relativity, both because they have to take these smaller time steps and it's just harder, but also because we have a huge number more orbits. Rather than a couple of tens of orbits, we've got tens of thousands. And the other thing that you get with these extreme mass ratio systems that's different from LIGO sources is that they're not necessarily circular. So almost all the systems we've seen with LIGO have been pretty good approximation circular orbits, with the exception of maybe 1 or 2 slightly eccentric cases. I'll try to play the video again here. This is more representative of what we might see with LISA in an MRI. It could be highly eccentric. In fact, this one is an inclined orbit, so there's, it's not even sticking to an equatorial plane or anything like that. And so there's much richer structure to the orbit, and that also brings with it a lot of extra challenges in terms of modeling. So that's one of the motivations for the method I'm going to talk about, the gravitational self-force method, in that it allows us to really build waveform models for these types of systems. But there is another kind of more imminent application, which is to the LIGO Virgo Kavli collaboration. So they're starting to see systems where the mass ratios aren't so close to 1. The most recent observing run saw systems possibly up as much as 26 to 1 or so. And that's starting to get to the region where the mass ratio is a small or a large number, depending on which way you count it. So to put this in, make this more concrete, if we look at the nice catalog of all of the systems that LIGO has seen since it started, you have one of these nice pictures here where each arrow represents the 2 black holes or neutron stars starting off, and then the end point of the arrow is the resultant merged object. And you can see there are a huge number of systems here now we've seen, some of which are neutron stars in orange and some are black holes in blue. And what I'm really interested in from the point of view of someone who works on gravitational self-force is just one of these, this one here, GW191219, 163120, which was, we think, consisted of a neutron star merging with a much, much larger black hole to produce a slightly larger black hole at the end. And the mass ratio of this system was somewhere in the region of 26 to 1. So getting into the region where the approach I'm going to talk about will become valid. And if you look at some of the papers that came out of LIGO at the time, they actually weren't 100% confident on this source. And part of the reason for that is that it's quite challenging for existing waveform modeling methods. And it's outside the region where many of the models that are currently used in LIGO data analysis are not really validated. So we're not 100% sure whether there are systematic biases in them or anything like that. So this system is another good reason why we might be interested in the self-force approach. So we now have 2 reasons. One is MRIs for LISA, and the second is potentially even kind of intermediate mass ratio systems for LIGO. So that's the why. What about the how? So how do we set up a self-force approximation to compute a waveform for example, for an MRI? Well, we start out with something like this figure up on the top right here, where you've got 2 black holes which might be spinning. One is much bigger than the other one, so M1 is the bigger one and M2 is the smaller one. They're in orbit around each other and they're radiating gravitational waves. Now, in principle, we could work out the waveform from the system by solving Einstein's equations, for example, using numerical relativity. But in practice, it's not really practical to do that once the mass ratio gets too small, too different from one. So instead, what we do is we take the space-time of the exact system, so the exact solution of Einstein's equations, and formally write it as a series expansion in a small parameter being the ratio of the small guy's mass to the big one. And here I've taken this series expansion to 2 orders in the mass ratio. The leading term here is just the space-time of the big black hole on its own, which might be a Schwarzschild or a Kerr solution to Einstein's equations. The sub-leading piece here, H1 and H2, are things that we need to figure out how to compute. And they are things that know about the small mass actually being a mass and distorting the space-time. So what we do to work out H1 and H2 is we take this series expansion, stick it into Einstein's equation, and expand out in powers of epsilon. When we do that, at leading order, we just find that this term is just a solution of the Einstein equation. It's a black hole. The H1 satisfies the linearized Einstein equation. This is now a linear PDE, effectively something like a wave equation, with some source terms that derive from the fact that you've got a small black hole moving around. If you go to the next order in epsilon, you then get on the left-hand side an equation for H2. Again, this is the same equation, so the same linearized Einstein equation, same operator on the left, but the right-hand side has something more complicated. It has something involving what we've got from first order. And as a technicality, actually what we do is we also add an extra term on here to account for the fact that the orbit is slowly evolving. And we do that using a 2-time scale expansion. So that's the framework for how you do self-force to solve the Einstein equations. For most of the rest of the talk, I'm going to specialize to the easiest case, which is the one that we've looked at so far, which is quasi-circular orbits with radius r0. And if we have spins, they would typically be aligned with your orbital angular momentum, although I'll show some slides at the end that removes that last restriction. So this is in principle what we do. We solve the linearized Einstein equation for H1 with some source on the right-hand side, and then solve the linearized Einstein equation for H2 with some source on the right-hand side. And it's this right-hand side piece that's hard work. That takes quite a lot of effort to compute this robustly and accurately. Once you've computed it, actually solving the equation for H2 is relatively straightforward. So that's really gravitational self-force in a nutshell in one slide. There are a couple of tweaks that we can make to this scheme to make it actually kind of converge better as a series expansion. And those are as follows. So what I've written down is a series expansion of the Einstein equation in the small mass ratio epsilon. We also have this Q, which is 1 over epsilon, a big number greater than 1. But it turns out to be better in the sense of more accurate to not expand in epsilon, but to expand in this symmetric mass ratio nu. And there are a few reasons you can think this might be the sensible thing to do. One is it kind of imposes an inherent symmetry in the system under interchange of M1 and M2. And imposing that symmetry turns out to make the approximation more accurate. The second thing we do is we don't talk about orbits in terms of radius, which is kind of a coordinate-dependent definition, but rather we talk about them in terms of frequencies. So we work with this thing x instead of r0. So x is some measure of the separation of the two of the binary, but it's more coordinate-independent than the radius. And so what we do in practice is whenever we compute something, for example, a function f of r0 and epsilon as a series expansion in epsilon for different values of r0, we convert that into a function of x and nu, basically just using the straightforward relationship between nu and mass ratio and between x and r0. So that's sort of a slightly technical thing, but it turns out to actually improve agreement with the kind of full solution even when the mass ratio is not too small. Okay, so far I've talked about solving the Einstein's equation, which was this slide here. That tells us about the perturbation to the space-time. But the other thing we need to consider is that this black hole here is not following a GD stick of the bigger black hole space-time, but is in spiraling. So we need to write down equations for the orbit of this small black hole around the big one. The way we can do that is if we think about the orbital phase, that's how far around it's gone, that is just given in terms of the integral of the orbital frequency. And in a minute on the next slide, I'll actually write down an equation for that orbital frequency. But before I do, it's worth just thinking about what ingredients from the linearized Einstein equations, H1 and H2, for example, are required to produce a waveform for an emery. So if we think about this waveform in terms of having an amplitude and a phase component, the phase is essentially the orbital phase, although there's a slight correction to that. And what goes into determining this orbital phase accurately enough, for example, for LISA? Well, I said we wanted order 1 radians accuracy. So we want to make sure that any error we make in computing the phase is smaller than 1, or smaller than order 1. And if you go through the analysis and figure out how does the phase behave as a series expansion in the mass ratio, well, it has a leading order piece, which is called the adiabatic order. This is relatively easy to work out because all it depends on is H1, and in fact it depends only on the bit of H1 that doesn't average to 0 over an orbit. This is the dissipative piece. That's relatively easy to do. It can be obtained from asymptotic fluxes by solving the Tarkovsky equation, for example, and avoids a lot of the messy details involved in computing the self-force. But that's not going to be good enough for LISA. And the reason is that there is also a mass ratio independent piece, which could be order 1. And we better get that right if we have any hope of having a waveform that's phase accurate enough for LISA. So this subleading piece called post-adiabatic order has several contributions. It has the bit of H1 that is conservative, essentially the bit that doesn't average to 0 over an orbit. That's harder than H1 dissipative, but still not so bad. And it also has this H2. In fact, there's only a part of H2 we need, but it's difficult to only compute that part. And this H2 is what we call the 2nd order self-force contribution. And if you remember back to when I was writing down the Einstein equations, this is the bit that I said was hard to find. So it's hard to find, but it is crucial if we want to get a waveform that's going to have the phase accuracy that we would need for LISA and for LIGO, for example. Okay, so that tells us that we're going to need H1 and H2. Let's go back to thinking about the orbits again. So I said that the orbital phase we can get by integrating the frequency. Well, that just shifts the problem to try and figure out how we obtain the frequency as a function of time. One way we can do that, the way we've done in this paper at the bottom of the slide here, is by starting from an exact expression, the Bondi-Sachs-Maxwell formula, which tells us that the rate of change of energy of the Bondi masses in space-time is balanced by the flux of energy of gravitational waves coming out of it. That Bondi mass can be related to the masses of the 2 black holes and the binding energy of the system. And so far everything is exact. We can now start to exploit the fact that we're working in perturbation theory and M2 is much smaller than M1. If we do that, we discover that this term can be neglected. Effectively, it appears at higher order in the mass ratio expansion than we need to go to. So that's good news. And we're just left with these 2 terms here. If we then go through and apply the DDT to each of these pieces, what we find is that it depends both on the derivative of the binding energy with respect to the time. And also this second and third term, which capture the fact that the mass and the spin are not fixed, they're not constants, they're actually going to evolve. So the black holes aren't just going to stay with their initial mass and spins, they're actually going to pick up some mass and spin as they evolve. Now, formally, these terms do appear at the same order in the mass ratio that we're doing in our calculations. So they appear at that post-adiabatic order. But we know from, for example, numerical relativity simulations that they're numerically very small. So as a first approximation, we can leave them out. This isn't fundamentally required, but it allows us to take a slight shortcut in our calculations. And in the long term, we do intend to add these back in, but for now, let's leave them out. So this now gives us, if we rearrange this equation, an equation for d omega dt is just f over dE. Okay, I seem to have a typo there. dE d omega. So in other words, we now have an equation for how omega changes with time. U here is retarded time, so we can just replace it with t. So we have this equation that tells us how omega evolves with time. All we need for that is this flux of gravitational waves and the binding energy of the system. And then once we have omega, we can solve for the phase by just integrating with respect to time. And it's in these two terms on the left here, the flux and the binding energy, that H1 and H2 crop up. So we need to compute H1 and H2 first. We can stick them in here, and then we can work out omega. And once we work out omega, we can work out phi. And so that's the framework we have for computing the orbit and the solutions to the Einstein's equations for within the self-force theory. We compute H1, H2. Once we have those, we can compute omega and phi. And once we have all of that, we're ready to go to produce a waveform. So if I go on to the waveform part, well, I said you can split it into an amplitude and a phase. As I said, the phase is just determined by omega, and omega was obtained from the fluxes. The amplitudes, on the other hand, are just the solutions H1 and H2 that we've already computed from the linear Einstein equations. Okay, so that's really it for the theory. Let's get on to having a look at some results. So let's look at some waveforms. So qualitatively, what we should get is something that looks a bit like this. We have a big black hole at the center, and we have a small black hole in orbit around it on a quasi-circular in spiral, getting faster and faster as it gets closer. And then associated with that is something which oscillates and grows in frequency and amplitude as a gravitational wave signal should. This is the qualitative picture that comes out. This is actually, it's accurate. It comes out of one of our calculations, but we can do more than just look at things qualitatively. We can actually start to think about comparing these waveforms against known results. And by known results here, what I really mean is numerical relativity simulations. So it's not possible yet to do numerical relativity in the extreme mass ratio regime, the 10 to the 6 mass ratio. But it is possible to start to get part of the way there. In particular, there are pretty nice accurate simulations up as far as mass ratio 1 to 10. And this is actually going to be comparing against one of the SXS simulations. So if you take that SXS numerical relativity simulation as a baseline, we have the black curve here, which is actually hidden underneath the orange curve. And the orange curve is the one that comes out of our gravitational self-force model. It looks very good in the early in spiral and quite a way in close to merger. If you zoom in right around merger, which is what you get in the bottom box here, you do see that it starts to, at the very end, starts to dephase, and eventually the model we have at the moment breaks down and can't quite do the merger. So this orange one is kind of the state of the art in terms of waveform generation with self-force. Prior to that, we had just the adiabatic waveform models, which I've included in blue here just to show that it really is a very significant step change improvement once you include post-adiabatic effects. So this is Q10. That's about as good as NR can do. Maybe they can now go to Q20 or a little bit more, but it's kind of in the ballpark of the limits of numerical relativity. And it seems that gravitational self-force waveforms are doing quite well even there. So it's worth thinking, well, how far can we push this? And of course, the ultimate limit is equal mass, Q equals 1. So if you look at that case, you get the lower waveform. So this is again a comparison against an SXS simulation, quite a long one for equal mass non-spinning system. The black is the numerical relativity signal, and the orange is gravitational self-force. So remember now we've started from...
Barry, 5 minutes.
Yep.
Just
Great, thanks very much. So we've started from an approximation, which is supposed to be a series expansion in the mass ratio. And now, quite remarkably, even when you evaluate that with mass ratio 1, where you have no real reason to expect the series even to converge, it does even capture quite well the behavior, although the dephasing is certainly worse close to merger. You can do more detailed comparisons. In the interest of time, I'll just go through these quickly. For example, you can look at the amplitude of that waveform, and it really agrees extremely well, basically to within the level where you can't distinguish them. There are oscillations, for example, in the numerical relativity signal that are bigger than the difference between the self-force waveform and it. And also, this slide points out that you can even do higher modes, so not just the 2-2 mode, but also 3-3, 4-4, and 5-5 also agree very nicely. You can also dig into more detail to see exactly how accurate the phase here is. And looking at the orange curves here for different mass ratios, you see that we're always below the 1 radian phase, even quite close, even right just before merger. So we're certainly kind of meeting the sub 1 radian phase accuracy, although maybe you want even 0.1 or 0.01, and we're depending on your requirements, we might not quite be there. Another way you can kind of measure how well the self-force waveforms are performing in comparison to numerical relativity is looking at this, what's called the adiabaticity parameter. So it's the time derivative of or 1 over the time derivative of the orbital of the waveform frequency. And on here we have solid curves representing numerical relativity measurements, and then we've got dashed curves representing what comes out of gravitational self-force model. And they do very well up until quite close to the ISCO, where the merger is about to happen, at which point the model we currently have diverges and breaks down. Okay, so that's kind of where things were as of the end of last year in this paper, which is on the archive. What I want to do maybe in the last 3 minutes or so is just give you a taster for where things have gone since then and where I think things are going. So there are a number of improvements we can immediately introduce into our model. First up is spin. So far, everything I've talked about has been for non-spinning systems. It turns out to be relatively easy to add spin. So in particular, if we want to think about the spin on the smaller black hole, the secondary, that's something which we can add perturbatively, and there's no limit on how big the spin of that thing could be. It can be almost a maximally spinning black hole. It's worth thinking about that spin as having a component that's kind of parallel to the orbital angular momentum and one that's orthogonal to it, because they feature differently in how you model them. So I should mention that this work is really kind of work by my student Josh, who is actually there with you guys at the moment. So I'm sure he'd be happy to add some more questions about that in person. So if we look at adding spin to a waveform, well, if we just really try and zoom in on the features by looking at an equal mass system not spinning compared to an equal mass system spinning, we see that the waveforms look very different. This is just comparing two self-force waveforms. And this is really to emphasize that spin can have quite a significant effect on the waveform. If we want to be a bit more quantitative, we can go back and start comparing to numerical relativity again. And this is somewhat preliminary, but we can see that if you have quite a highly spinning secondary, 0.8, and a mass ratio of 6, that we do actually capture the signal very well with the self-force waveform model. And just to convince you, if you go back and you remove the spin from the self-force model, you get the blue one here, which is quite significantly worse. We can also capture spin precession. So when the spin is not parallel to the angular momentum, the orbit precesses, and you get a lot more rich structure. And this plot is just representing the fact that we've now added that into the model as well, although in a preliminary way. So that's spin effects. The last thing I want to mention is improving what happens near the merger. So that near the merger, we saw that our model seemed to just suddenly stop and was certainly starting to get dephased from the NR signal. So if you zoom right in on that region, you see that about 3 or 4 cycles before merger, our waveform stops, and it's about about half a radian out of phase at that point. So what's going on there? Well, one way we can understand it is from this adiabaticity parameter plot. This tells us how fast the orbit is evolving. And you can see that our dashed curves are shooting off away from what they're supposed to be at very high frequencies, so to the ones close to merger. So that's suggesting that the whole approximation that the orbit is evolving slowly and adiabatically is breaking down. And you can kind of even see that from this graphical picture that initially, when they're largely separated, the orbits are slowly evolving, but as it gets closer to merger, it's spiraling faster inwards. We can formalize this a bit more carefully, and we discovered that that expansion of the phase in terms of integer powers of the mass ratio breaks down. And the trick to get around that is to realize that actually there's a different scaling with the mass ratio in the timescales of the system. If you go through the analysis, you get new equations for the phase and the frequency, which now have fractional powers of the mass ratio. And this is, so this is an approximation that's going to kick in at some point once we get close enough to the merger. What close enough means, well, one way we could measure it is if we go back to those waveforms I showed before. If we think about when those transition effects are as important as the effects that we're including, we get these red lines here, which tell us that to the right of these, our existing adiabatic model really isn't cutting it. It's not including all of the necessary physics that it needs. But the good news is, I've just shown you that we have the equations that we need to use to the right of that line. And if we actually use those, so this is work done by Lorenzo and his supervisor Jeffrey, we get these figures here. So if we look at the Q10 case, without the transition, we see that it suddenly stops at the ISCO, which is the gray line on the right here. If we add the leading order approximation to the transition, we can get right through the ISCO, although not all that accurately. If we add the first subleading term in transition, we suddenly start to do awful lot better. And we're starting to match the signal almost to merger. I should note that we actually plan to add about, I think it's 7 orders in this transition expansion. So we're expecting to get an awful lot more accurate as we do that. Okay. So I won't really talk about the plunge, but once you get past this region where you're transitioning from an in spiral to a plunge, you're then
we're at 5 after. Just heads up.
Okay. Yeah, thanks. I'll finish now. So I'll skip that slide and maybe just go on to some conclusions. Outlook. Conclusions are we can produce waveforms for non-spinning systems with arbitrary mass ratio very fast, millisecond kind of timescales. We need to add transition and plunge. We need to add more physics in terms of spins, eccentricity, things like that. And there's an awful lot more work to do to make this into a kind of a complete model, including all of the physics that we need for a waveform generation. Okay, I'll leave it there. Thanks.
Thanks, Barry. Let's see, questions. So we've got Sam in the middle here.
Hey, Barry, it's Sam Krala. This is just a comment as someone who's followed this field for some time. well done. These are some pretty spectacular results. If I didn't know you so well, I think you cheated or something to get such amazing agreement.
Thanks very much.
Just kudos.
Well, it's one of those things in hindsight. I mean, it looks, we say it's remarkable and surprising, but actually we know that this is what should have happened, because we know that what we're leaving out is the next order in the mass ratio, the phase. And so we know if the mass ratio is 1 to 10, then it should be a factor of 10 smaller. So it is remarkable, but to be honest, it's actually what you would expect in hindsight.
Oh, yeah, let's go to no. And then...
Yeah, so thanks for the nice talk. Yeah, so I mean, these results are really impressive, the matching between these moderate mass ratios. So I'm wondering if there's, if you expect that once you go to more generic orbits, we have, you know, both bodies spinning and precession and stuff, if you expect the matching to still be at this level, or if there's reason to suspect that, you know, restricting to these equatorial orbits or so forth might make the match particularly good for these moderate mass rates.
I guess we can't be sure until we do it. The hope, I mean, the framework is designed to be able to extend to kind of those generic cases. Some things we can do quite easily, so we'll have the answer pretty quickly. So we have the spin on the small black hole generically now. We can add linearized corrections to the spin of the big black hole. So for small spin in the big black hole, we can add that in kind of the time scale of a couple of months. We can add small eccentricity, again, kind of in a linearized approximation on a time scale of a couple of months. So we'll be able to add those, answer those questions quickly. For more generic cases, the hardest thing is going to be going to the case where the big black hole is spinning significantly, where it's occur. A lot of what we've done is kind of has been built on that being a Schwarzschild solution. So that'll be a lot harder, but we kind of have an idea how to do it, but it's certainly much harder. In terms of how well it will match, I think the hope is that it will do as well, but I don't honestly know for sure.
Yeah, thanks.
Hey, Barry, thanks for that talk. I just have a question. This is Luis Leonard. As you try and push this to the nearly equal mass ratio and deep into the merger regime, I mean, some of the concepts that are used explicit in this construction, like the binding energy, I mean, is it clear that we have conceptual control on them to keep relying them? Because at some point we're going to get to the standard old problem of GR. We cannot even define what the local mass is. I mean, is this, you have a feeling that may get in the way?
So, I mean, within the self-force approximation, you have relatively good control over a lot of that sort of ambiguity. You mentioned the binding energy, which is the one which is probably the trickiest, and if I'm completely honest, the one that is least well understood. So we did compute the binding energy is something that we have computed the self-force correction to, but there are ambiguities in that for sure. It may be a matter, I don't know if Adam Pound is here or not, but he may be able to talk more to that. But the binding energy is the one where we're least confident with those sorts of ambiguities.
I can chime in if you want. I don't know if you can hear me.
Yeah. Yeah, speak up a little.
Oh, okay. So this might be a really basic question. When you write Einstein's equation, what exactly do you put for the stress energy tensor? Is there one contribution for each black hole? And do you have to correct that as you go up?
So at leading order, you basically put in a point particle. You have to do so this TAB here for epsilon1 is a point particle, it's a delta function. In reality, we do things a little bit more carefully, and we account for the small thing not just being a point particle, but being a black hole. And that's kind of captured by these HS things in here. So you can, in practice, when you're doing the numerics, you can treat things as point particles, but that's been a derived result that's come from a kind of a more careful matched asymptotic expansion, where you take the small black hole to shrink down in size in a certain limit.
So basically, T has the point particle, and then all corrections are captured by the HS type terms.
Yeah. Well, T is a point particle. You can, if you have a spinning black hole, then you'll also have to incorporate that into T as well. That's kind of as a derivative of a delta function. But that gets pushed up into this epsilon squared piece. So it does have to be added. And that's what in Josh's spinning waveforms, he added that. He said.
Thank you.
Raphael.
Hi, Barry. I have a question. You had over there somewhere some conservative part of the metric, but you didn't define that. And this is kind of one of the questions that many of us have been going through, especially comparing with post-Newtonian. So what do you guys define as conservative here precisely? So
at leading order, it's easy to do it. You can relate it to the time symmetric and time antisymmetric pieces.
Let's say I have a green function. So you're saying you do retarded plus advanced divided by 2?
So yes, at leading order, that's what it is. So in kind of the H1, advanced plus retarded is conservative and advanced minus retarded is dissipative. At subleading order, we haven't really been able to define it properly. And so actually when I say H2 here, I kind of briefly mentioned that we actually have to compute the whole thing because there's no, well, we tried, but there was no good way to just extract some meaning of dissipative once the orbit is spiraling.
And this includes all the so-called tails inside these conservative and dissipative pieces.
I think so, yes. Yeah.
If I ask you whether you have memory terms in there, you wouldn't know what to say.
I think we do. I think we can actually. I think Adam may have computed the memory terms, or someone has computed the memory terms from this framework. Yeah.
So in principle, at second order in cell force, you will start seeing all these nonlinear tail and memories coming out of your conservative and dissipative solution. Correct?
I think so. Yes. Yeah.
Raphael, I'm going to move on for a moment. We've got one more question, and we're about to run out of time in the question period. So
I'm the next speaker. Anyway.
Yeah, I know. So exactly, you'll get your chance. So we'll move on to Adam.
Thanks. I didn't actually have any questions. I was just going to comment on previous questions. So if we're short of time, we can leave.
No, please go ahead.
Okay, so about the binding energy. So the binding energy we do actually have total control over, but it is ambiguous. It depends on your choice of slicing, how you connect up your slices to the horizon and to scribe plus. But we are actually measuring the binding energy directly from the bonding mass, which we can measure, and the horizon mass of the big black hole. So we do have perturbative control over that order by order. But it is a gigantic headache, as Barry alluded to. About the memory, we have calculated the leading order memory. We could calculate the subleading order memory. We haven't done that yet. About defining conservative dynamics at second order, yeah, that's a gigantic hassle. We haven't done that properly. I'll disagree with Barry a little bit about the dissipative piece. So that we actually haven't calculated the whole thing. We have only calculated the piece we need, right, Barry? I mean, we've only calculated actually the easier piece.
Well, I guess we solve for the full thing, but we only actually use.
But we don't because we discard all the m equals 0 modes, right?
Ah, right. Yes. Okay. Currently, yeah. Except for the L equals 0, m equals 0.
Yes, which was the biggest headache.
Yeah, that's true.
Adam, can you give me a yes or no answer? Do you agree now with post-Newtonian to second order in cell force at 4 p.m.?
We don't know because of the conservative versus dissipative split.
Ah,
I have a student working on it. Give me a year.
A year.
Perfect.
A whole year.
Perfect end to the question period.
Our
Thanks
priority is getting
again.
good waveforms right now. Everything else is.
Oh, we have a big discussion about conservative and dissipative in post-Newtonian. That's why I was asking.
Raphael, you're eating into your presentation time, just so you know.
Yeah, I know.
So,
well, I thought
thanks.
this was whole discussion.
No, it's great. It's actually fabulous. Thanks, Adam.
Okay.